There's a second form for the fundamental theorem of calculus, and I'd like to show you an example of where this can be valuable. All right, so let's start with calculating the indefinite integral of sine of x squared dx. So if we do that, sine of x squared is a composite function. The inside function is x squared, so it would probably try to use u substitution. All right, and we'd let u be that inside function x squared. Then remember we'll replace the x squared with u. We'll have to replace the dx, so we'll have to calculate it. In order to do that, we'll take the derivative of u with respect to x, du dx, and that would be 2x. And then I could multiply both sides of that equation by dx. And what that would give me, dx times the derivative of u with respect to x, is the differential du. So I would get du is equal to 2x times dx. And then I could solve for dx by dividing both sides by 2x. And if I do that, all right, I'll have dx is equal to du over 2x. All right, now making these replacements, this would become the integral of sine of u times dx, which is du over 2x. And at this point, I'm stuck. I can take out the factor of 2 in the denominator, and we have 1/2 times the integral of sine of u times du over x, but there's nothing I can do with the x. And so at this point, I am stuck. I cannot go any further. But there's two things I should say here at this point, is that I could study this function a little bit more, this antiderivative a little bit more, using the second fundamental theorem of calculus, or the second part to the fundamental theorem of calculus. And in Calculus 2, you'll be able to do this, you'll be able to approximate this function by using power series. And you'll see that in the next semester. All right, so here's what the part 2 of the fundamental theorem of calculus looks like. All right, it says that if f is continuous on an interval, then f has an antiderivative, all right, on that interval. Okay, and in particular, if a is in the interval on which f is continuous, then the function capital F defined this way, all right, integral from a, the point in the interval, to x of f of t dt, all right, is an antiderivative of little f. In other words, capital F, the derivative of this function, is little f of x. All right, so that if I differentiate the integral from the definite integral from a to x of f of t dt with respect to x, I get little f of x. Now that seems kind of like double talk, because it says, well, we have an antiderivative, but in order to calculate this antiderivative, you're going to have to antidifferentiate it. If you couldn't find one to start with, as was the case with sine of x squared, where do you go from here? All right, what can we do? Well, there's a way of dealing with this, but I wanted to remind you of something else here. If this is that derivative of capital F. If we'd evaluate capital F at A, we'll have to replace every instance of x with A. In other words, capital F of A is going to be the integral from A to A of little f of t dt, and that's going to be 0. All right, we've seen that before. Okay, so now let's do the following. Let's go back to our problem. We wanted to find an antiderivative of a sine of x squared, a function that has sine of x squared as its derivative. So let's look for a function f such that f prime of x, all right, is sine of x squared. And then also, when we do that, we should come up with a constant of integration. But let's assign that constant in such a way that so that f of 2 is equal to 3. That f of 2 is equal to 3. All right, now let's see, how can we do that? Remember that one way to get an antiderivative of little f is to calculate a definite integral from a to x of little f of t dt. All right, in this case, all right, this is what the fundamental theorem of calculus part 2, all right, tells us. So, and this would give us an antiderivative of little f. So if I do that with sine of x squared, so sine of t squared dt, all right, that should give me an antiderivative of sine of x squared, a function who has sine of x squared as its derivative. Now here's what I want to do. I'm going to use this value as a. So this will be from 2 to x. Of course, sine of t squared would have to be continuous on an interval containing 2, and it is. It's continuous everywhere. All right, so notice that I'd have that. This now, just with this, now, f prime of x is equal to sine of x squared by the fundamental theorem of calculus part 2. So we have the first part. Okay, all right, now there's one more thing that I should keep in mind. If we look at f of 2, f of 2 is going to be the integral from 2 to 2 of sine of t squared dt. All right, well, I'm integrating from 2 to 2, so this would be 0. Well, I don't want it to be 0. I want it to be 3. I want f of 2 to be 3. But right now, the way things sit, it's going to be 0. Well, what I can do to make it 3 is simply add 3 to it. So then that f of 2, f of x, is going to be this integral from 2 to x of sine of t squared dt plus 3. Now if I evaluate it at 2, I'll get this integral that's worth 0 plus 3. I'll have the right thing. So here would be that function. All right, now how does that help you? All right, how does that help you? That doesn't show you anything. All right, well, it does help because here on Mathematica, I have produced a plot of this function. This is a plot of capital F of x. All right, now let's see, how did we do this? All right, well, you don't have Mathematica perhaps, but there are other ways you can do this. And by the way, notice that when I evaluated at 2, I get 3. Okay, how did I do this? Well, there's a couple ways. You could go back in and use Wolfram alpha. And here's what I have for Wolfram alpha. I integrate sine of t squared with respect to t from 2 to x, and then add 3 to it. And notice here are graphs that I've produced on Wolfram alpha. Just you could do that on your computer. All right, this one goes from -3 to 3. This one goes from -5 to 5. But notice that they're basically the same thing. We have sort of a restricted version here. We just have about this much from -3 to 3 up here somewhere. on this first graph, and this was just has a little bit more. You could even do this. This is a little more time consuming because it's this slower, but here's a plot that I produced on a TI-84, okay, and here's the plot of that function of f of x, all right, and it goes from, I think we're going from -3 to 3 here, and here's how I produce the plot. I set y1 equal to fn int, all right, that's function integral of sine of x squared, all right, as x goes from 2 to x, and then I close that, I ended that integral function plus 3. Okay, and to get to this fn int, if you go to math and then go down to math 9, here it is, math 9, and you could produce the very same function on your calculator. Notice that when x is 2, all right, y is 3. So this would be a way of using this second fundamental theorem of calculus, all right, to actually examine antiderivatives of functions where you can't anti-differentiate it.